Hello YouTube, here is Anatolii. In this short video I would like to show you a Fourier analysis, pretty simple one. So we'll just take a square wave and find the Fourier coefficients for it. So imagine if we have a square wave like this. So okay, these are the axes and we have a square wave. Okay, looks fine to me. And let's put some values, so it will be varying from 0 to 1, and here from minus pi to pi. Obviously this and this points are minus pi over 2 and pi over 2. Okay, so what we need to do, we need to find two coefficients. So it's A of harmonic orders and B of harmonic orders, and both of them would be an integral of our function. In this case, this function is our square wave multiplied with cosine n x dx. And here it will be the same, but instead of cosine it will be sine. Okay, so when we have symmetry, we can have two different types of symmetry, right? In this particular case we have a symmetry around this axis, so basically if we calculate Bn, this integral will turn into 0. If we have another type of symmetry, if we have something like this, then this integral will turn into 0. Okay, so let's try and take a look. Let's zoom it. So we'll calculate this integral. So we have an integral and our function is basically 1. And it is 1 between minus pi over 2 and pi over 2. So the limits here we put minus pi over 2 and pi over 2. And the whole period is from minus pi to pi, which is 2 pi. Okay, and then we multiply it with cosine n x dx. And now we just need to solve this integral, which is very simple. So what we need to do, just, okay, we'll start with 2 pi over this value, n, and then it would be multiplied by sine np over 2, and pi over 2, this value, minus sine minus n pi over 2, which is this value. Okay, if you don't remember, if you remember, so sine of minus x is actually minus sine of x, right? So this whole expression would become 2 pi over n, and here we'll have 2 sine n pi over 2, which will lead us to 4 pi over n sine n pi over 2, and where n is our harmonic order. Okay, to make it full, we also need to put some sign here and range it from 1 to infinity. And if we make one step further, so we can check that sine of pi over 2 is actually equal to 1 sine pi, 2 pi over 2, which is just pi, it's 0. Sine 3 pi over 2 is minus 1. Sine 2 pi is 0 again, which means that this expression we only need to calculate for n, which is 1, 3, 5, 7, and so on, all of the odd values. So yeah, that's how it's done. Okay, and what if we want to test our expression and figure out and confirm if it's truth or not, if we calculated it right or not? Okay, so let's make a simple example in Python and see how we can do it. So, okay, first of all, we need to import a couple of libraries. Obviously, NumPy, SNP, and matplotlib. Import matplotlib pyplot splot. Okay, the other thing I want to do, I want to import sine, cosine, and pi from numpy. So I don't need to use this NP all the time. I want to use these simple functions. Okay, so the expression we have here is it's sum from 1 equals to 1, 3, 5, and so on to infinity, and it is for pi over n. Yeah, right? Right. And here we also have sine n pi over 2. And I think that's it. So this is the expression we want to check. There's another thing. So if we want to plot it as a waveform, not as Fourier coefficients and not as the spectrum, we need to multiply it by cosine of omega. I think here we should put n omega x, something like this. Okay, so let's dive right into it. And first of all, okay, I want to make some x, which would be a line space from 0 to yeah, let's try 1 at this point, and I want to have 1000 points. After that, for n in range, let's put 100 here. And let's make our square wave. Okay, just need to shut it down. Square wave, which would be zeros like x, where I create the same type of array as I have x here. And then I write it down, x plus equals 4 times pi over n times sine n pi over 2 times cosine n times, okay, let's make it 2 pi and t. And then I just plot it. So let's try plot x, this one, yeah, square wave. It's not x here, it's square wave. Okay, let's see if I get it right. No. Obviously I need to make range from 1 to 100 to 99. And now, yeah, why did I put t here? It's x. Voila! Yeah, there is something else. So we get it from 10 to minus 10 for some reason, and what could be the reason of this? Okay, so let's also put grid here, so it looks a little bit nicer. And what we also can notice that we also get the Gibbs effect here, which is, well, I would say pretty good, no? And if I decrease the number of harmonics, or let's do something like this, so let's, yeah, put all of our harmonics here. Looks pretty nice though. What do you think? Okay, so yeah, that's it for now. As I promised, that it was very short, so don't forget to subscribe, put likes, and write some comments, and see you later. Okay, it is actually not the end of this video, so why won't we plot the FFT, the spectrum? Okay, and for this, it's not really difficult, so what we need to do, we just need to create two empty arrays, harmonic, order, for example, and amplitude. Harmonic amplitude, let's call it. And now we need to run the for loop again. So we run the same for loop, but here we don't actually put this thing. And this expression would be the harmonic amplitude. So we just create an array of all of the amplitudes for all of the harmonics in this order from 1 to 100. Yeah, and don't forget it should be absolute value. And another one, okay, let's also create an array of harmonic order. And let's run it. Okay, no error, which means it works. Let's try to make a bar plot, and x here would be harmonic order, and height, I guess, would be harmonic amplitude. And also let's put the grid. Okay, so we have some result, so let's try to check it. I will check it in Plex. Just make a pulse with from 1 to -1 with the frequency, let's put 1000, and run it. Okay, let's also put first 10 periods. So now let's put the FFT here. Our frequency is 1000, and evaluate 100 harmonics. To me it looks similar. I don't know about you, but at least, okay, the first one is a little bit more than 1.2, 127, then okay, third one 0.42. Let's check. So harmonic amplitude 0, okay, 127, yeah, 2, 0.42, and one more, 4. Here it starts from 0, so it's actually fifth one what we put 4, 0.25, 0.25. Yeah, so now I think that's the end of this video. Okay, thank you for watching.